Hi there. Let's continue with what we started. We started with a buffer. So let's see this question. Calculate the pH of ammonium chloride 1.5 molar given and ammonia 1.2 molar given. And does the volume matter to be a buffer and what it is, right? So let's see that one. Ammonium chloride. And we know that ammonia is the base and ammonium chloride is the conjugated acid, and then cancel the chloride, it's no use. And now we can write this ammonium and ammonia as a buffer, because the buffer has two components, a conjugate acid or a base of a weak acid or base, and its other component, acid or the base, right? So two components, weak acid or base with its component, its conjugate component, it'll make the buffer system. Now, here we can, before we do the calculation, let's do the formula here. And it's a equilibrium with proton, so see the left and the right is balanced, and you can write it this way or you can flip this too depending on that one. See, conjugate acid, the other component is the base of it, so this makes the buffer, each component is satisfying for the proton gain or proton lost, right? Now, so we can do 1.5 molar here, 1.2 molar here, that's given. And the pH is pKa plus log base over acid, and this is the Henderson-Hasselbalch equation. So don't be scared on this one. So you plug in the pK value which is given, and the log base is 1.2 in this case, and acid is 1.5. Now solve the inside the bracket first and take the log value, add into 1.25, you will, yes, you're going to end up here 9.15. Now look at this magic. 9.25 is when it is 1 on 1 of the two components, 1 to 1, that will be at equilibrium. That is the pKa. Now we have 9.15, which is a little less or towards 0 side, and that's bit acidic. We can prove it because you look at the acid molarity is higher than the base molarity of the buffer solution. So that's how you justify your answer. Now let's look at other situations. If the pKa is equal to the pH, that's the base and the acid components are equal, 1 to 1. And if the base is larger molarity than the acid, the pKa will go towards the 14 side. If the acid component is more, molarity is higher than the base, the pKa will more towards the 0. That's how you guesstimate, right? So it's a good idea to have that picture. Is it big A, is it big B, or is it AB equal amounts, right? Okay. So let's move on to the next question. My next question is what's this one? Triethylamine. Now, triethylamine, and let's see, it's conjugate acid. That means triethylammonium, right? So we should be given actually Kb or Ka. Let's see. So triethylammonium, 3 methyls, NH, ammonium salt. And it could have been come from chloride, right? And then it equilibrate with the base, which is a weak base is triethylamine, and the proton. So the left and right is balanced with the number of atoms and the charges. And that's the buffer equation. That's the two components each side, which each side can take or give protons. That's the role, or that's the regulation of the pH, right? So we can do a rice table, or we can do a RBCA, like Royal Bank kind of thing. So that means before, change, and after, sometimes we call it. Now we can plug in the moles, because the moles also fine for this type of rice table or RBCA tables. And I'm just going to jump to the very end because it's at equilibrium already. 0.10 moles for conjugate acid, and the weak base is 0.05. Plug into the Henderson-Hasselbalch. pH is pKa log base over acid, right? Never change this one. So the pKa should be, yes, it should be given. I think he forgot. 9.8, just plug in that one. And log base is 0.05 and acid is 0.10. We know where it's going already because acid is larger, right? So solve the within the bracket, take the log value and get the final value is 9.49. Now the pKa is 9.8 when it is 1 to 1. We are sitting at 1.49. So that means to the acidic side. Why? Because acid is more than the base, right? It works as a base, and we can also see which side it's swinging into, right? Okay, so if you have more specific questions, send in. Don't email me, just put it to the comments below, and it's better so somebody will copy that for me, right? Okay, so let's go here. So you are given sodium hydroxide 0.001 mole added for the above buffer, and this is what you want to do. This is an easy one rather than going into the rice tables and yada yada. So see, if it is a base, add the base onto the base B and minus that amount to the A, the acid. That makes sense, right? So you can do it with this equilibrium equation, or you can just do the math. If it is MCQ, you're rushing into the finishing exam, do the equation only. See, because we added a strong base, add to the base that same amount minus the acid the same amount. Now finish the within the brackets, take the log value and add into the pKa of the original one, right? So now original pK is 9.80, and then let's take this value. Yeah, finish the bracket inside first, and you end up with, yeah, minus 0.29 and then 9.80 put together, so it's 9.51, and it's gone to 9.51. So your benchmark is actually 9.49 from the above one, right? So that's what you measure, because the buffer originally wasn't sitting at pKa, it was sitting at this 9.49. That's kind of the benchmark. Now you throw in some base, it should go towards the base side. That's what exactly happened. More base added, now it's 9.49, right? No, original base point is 9.49. Now it became 9.51. Does it make sense? Okay. So the part B of the same question, add HCl, strong acid 0.002 moles. Okay, go back to the original Henderson-Hasselbalch. Now this time it's a strong acid minus the amount from the base and add the mole amount to the acid. So don't worry about the total volume, because that's going to be cancelled out from the top to the bottom, right? So 0.001 minus for the base and 0.002 actually. 0.002 added to the acid. So solve the within the brackets first, take the log value, added into the 9.80. So now we get our benchmark is 9.49, this original buffer before we add the acid. Now we added it, it becomes 9.47, which is little bit acidic, right? Few points. So that's still valid. The buffers are good, plus or minus 1 pH. So this is less than 1 pH. So it behaves as a buffer. Any questions, please put it in, send it in, and we'll solve it.